Engineering 305, example problem 811. We've got a 16-foot long, simply supported beam carrying a uniformly distributed load, 500 pounds per foot, and a concentrated load of 1,000 pounds, as shown in figure 820. So I put the figure there. 1,000 pounds, 6 foot from one end, so it's not centrally located. That makes this a little bit different, but it's fine. The beam is rough sawn, which means it's a nominal 4-inch by 8-inch, or it's 4 inches by 8 inches, as opposed to a normal 4 by 8 would be 3.5 by 7. Don't worry about that. Don't worry about that. 4 by 8-inch wood beam made out of air-dried Douglas fir. They give us the Young's modulus for that. That's also in the front cover of the book, and it's not a bad it's not a bad value to use for the cantilever beam lab. Determine the deflection at the center of the beam. There's our problem. Determine the deflection at the center of the beam. Well, this is the section on cartoons. And so the first thing we have to do is let's take a look at the cartoons that are available. We've got simply supported. I just copied the simply supported ones that are appropriate. And you can see I've got a simply supported one here where we've got loading that's taking place off-center load. So that's kind of what we have. Here's a center load where that's at L/2. That's not what we have. So we can use situation 5 and situation 7, which is a distributed load. So let's try to break things up into their terms. We need to figure out what A and B are. And then the other thing you can see here, there's a little qualifier. B is less than A. So it's loaded on the right side of the beam, and ours is loaded on the left side. But that's okay. We're going to take our problem and flip it around and look at it backwards. So we'll have to start doing all those things. So let's first get rid of that, and we're going to move our figure over to the side. And we'll start saying, look, this load that we've got, which is this simply supported distributed load, and then I've got a point load like that, is going to be equal to that beam with a distributed load and plus that. And now the way they're defining it, we're going to do, it's, in one sense, actually, this is pretty easy because if we looked at the beam, if I drew the beam this way and it runs into the page and my load was here, right? Then if I looked at it from this back side, oh, I got to get rid of that image. Not that image. I'll get rid of that one too. Oh, my goodness. So if we took, see if this helps. If we took this view and we rotate it to the end, then here's our end view. And then from the other side, I'm going to look like this, where now this is my short side. So whether I look at it this way or look at it this way, that makes the difference of how B and A get distributed. So we're okay. Now, the other thing about this that's interesting is I'm going to say we're looking at the deflection at the center. So when I flip it, I don't have to worry about B's and A's, and those things will kind of go away. So the first thing, what's the deflection at the center from that load? Well, I'm going to go back to my trusty dusty equations. And case 7, my maximum deflection is at the center, and it's minus 5WL to the 4th. I'm going to write that down behind this. Minus 5WL to the 4th over 384 EI. All right? Okay, that's kind of a mouthful. Then, now what about this one? And here's B, and here's A. Let's take a look at the problem figure. That B is 6 feet. A is equal to 10 feet. And you know, I'll start, maybe I should have put in some values here. This is 500 pounds per foot. And this is, oh man, you know what? I'm going to get into a units nightmare here, aren't I? This is 1,000 pounds. I really probably want to change all of this around. So I'm going to change this load to 60 pounds per inch. And then I'm going to change 6 feet to 72 inches. And that to 120 inches. All right. That might help me a little bit. I've already got that one. Now I still have to write down this deflection. Delta at the center is equal to, and I got to put my equations up there, 3. I want to know the displacement at the center, but that's not the maximum, and that's okay. I'm not worried about the max. They asked me about the center. That's equal to minus P B 3L squared minus 4B squared. 3L squared minus 4B squared. All over the quantity 48 EI. All right. So now if I want my deflection, it's just delta at the center plus delta at the center. Maybe I should have used better variables. Equals minus 5 WL to the 4th over 384 EI plus a minus PB 4L squared minus 4B squared over 48 EI. Now, W is 60 pounds per inch. L is equal to, it's 16 feet. That's 120 inches plus 6 times 12, 72, 192 inches. $16. Yeah, okay, I'll buy that. So I got B shows up in this equation. B was equal to 72 inches. So I know W, L, E and I. E, I'll put that at the top. E is equal to, it was 1900 PSI, I think. Let's show the problem statement. E is 1900 KSI. Good thing I checked. Good thing you guys keep me somewhat honest here. KSI. I is equal to base height cubed over 12 equals, oh, we can calculate that. I think I got everything. Oh, I need P, which is just 1,000 pounds. I've got L, I've got B squared, I've got L, I've got E and I. I'm all set. Just punch it in and go. Calculator work, so you guys get to pause. There you go. I calculated the first one, I got 2.27 inches. I calculate the next one, I get minus 7/16 of an inch. Okay, a little less than that. Minus 0.416 for a total of about 2.7 inches down. Now, I always want you to think about answers, right? And I know I don't do this every time, but I really do want you to think about answers. This answer is 80%, I'll say it this way, of my deflection comes from the distributed load. Does that make sense? Well, let's think about this. I have 500 pounds per foot times 16 feet. 500 pounds per foot times 16 feet. I don't know if I was abbreviating that or right now. 8,000 pounds. 8,000 pounds from my distributed load. P was equal to 1,000 pounds. So, yeah, this is most of my load. Most of the deflection. Now, I may want to even think about that farther. I say that actually creates, well, if this is almost 1/5, it's maybe closer to 1/6, but it's only 1/9 of the load. So this is actually, because of its location, it's got a disproportionate effect even though it's really small. Loads in the center you really pay for. Loads out on the end, they're not so bad. All right? Kind of interesting stuff. Kinda. All right. That, we almost have to go back and do a comparison to use integration techniques to see if that's good or not. So, but don't worry, there's more. About to work on 812. Have a good one.